coming. Okay, it's a pleasure for me to introduce you Professor Rejmak. He's working in the Institute of Physics in the Polish Academy of Science in Warsaw. A little bit to describe what he has been doing. He was doing the PhD thesis with Professor Eva Rosławik, the Institute of Catalysis in Krakow. Okay, there I think maybe also he was making some internship with Professor Sauer in Berlin. And now he comes here, where he was working still in this aluminosilicate cements. In cements, he did some NMR calculations on cements that are quite well put it in the bibliography, and also we worked in yeelimite, these aluminosilicate cements that are today the new cements and done by the first company, and he was making some characterization of the structure that are now settled into the industry and so on. So that is very important work. And since then, he has moved to this institute, and he's going to work a little bit, continuing in this aluminosilicate, working on computational studies of blue and red ultramarines. Please, the floor is yours.
Thank you very much for the introduction. It's a pleasure for me to be again in Donostia after 7 years break, I think. So as it was told, I am essentially a computational chemist who tries to survive among physicists. Currently, I am employed in the experimental group. So one of my tasks is to support the experimental studies done by my colleagues, mainly on transition metal complexes with potential pharmaceutical applications. I also try to do some other projects, and today I would like to tell about one of these. So ultramarines, as probably many of you know, are blue pigments. They occur in nature as mineral lazurite, which is the main component of metamorphic rock lapis lazuli. The main deposits of high-quality lazurite are located in Afghanistan, and they were exploited there since antiquity. And from there, lazurite was imported to the Middle East and Europe, hence the name ultramarine from Latin ultramare, beyond the sea. So it used to be one of the most expensive pigments until until the beginning of the 19th century, when the method of synthesis of ultramarines were developed in France. And since then, it is one of the cheapest pigments. So in the end of 19th century, even poorly paid painters could afford it. I was once corrected that Van Gogh in Starry Night used Prussian blue, but as I checked on Wikipedia, he used a mixture of pigments, Prussian blue, cobalt blue, I think, and ultramarine, so I decided to keep this picture. So the source of blue coloration in ultramarines is a 3-sulfur anionic radical, which is entrapped in sodalite lattice. Sodalite is aluminosilicate crystallizing in a cubic system. The ideal sodalite has this stoichiometry. So its lattice consists of the alternating silicon and aluminum tetraedra, forming these truncated cubo-octaedra, so-called sodalite cages. The hexagonal faces of these cages are occupied by sodium cations, and the center of these cages is occupied by chlorine anions. So there is a variety of solids with having topology of sodalite, where one of all of these elements were replaced by something else. Ultramarines are essentially sodalite, in which about half of the cages is occupied by this blue S3- radical instead of chlorine. There are also some other possible anions, and part of the sodium can be replaced by calcium or potassium or other methods. Why I was interested in this topic, so there is a lot of experimental studies on ultramarines. There is a lot of computational studies on isolated polysulfide species, both DFT computations and using advanced methods of quantum chemistry. However, up to date, there was no computational studies on realistic models of ultramarines, and I wanted to fill this gap. To be honest, recently I encountered this paper in American Mineralogists from 2012, where they did, I think, the first periodic DFT studies on lazurite to support some experimental data, but quite few details is given in this paper. So apart from the mentioned S3- radical, many other polysulfide species which are usually unstable in normal condition can be entrapped in porous aluminosilicates, and then they can be quite conveniently studied. These polysulfide species are interested both due to their, not only due to their optical properties, but they also occur as short-living intermediates in various reactions of practical importance, like electrochemical processes in metal sulfur batteries, in organic synthesis, in some biochemical, geochemical, or astrochemical processes. So they can be stabilized in these aluminosilicate matrices and then studied with quite conventional spectroscopic methods. So I started my studies from, first I constructed in total 12 structural models of ultramarines starting from the available experimental data. In this data, the structure of trisulfur radical is not well resolved, so I considered several possible initial orientation of S3- radical within sodalite cage. I consider 3 types of stoichiometry, so either I replaced one chlorine with S3- or both chlorines, or I removed single sodium cations and chloride anions and put single S3- radical. I optimized these structures at DFT level using gradient PBE functional. Then from these structures, I cut finite cluster models, saturated dangling bonds with hydrogens, and for these finite models, I performed calculations using hybrid functionals and atomic center Gaussian basis sets to study spectroscopic properties of interest. So I used hybrid Becker-Philip functional to calculate G-tensor for electron paramagnetic resonance, and long-range corrected Becker-Philip to calculate electron excitations to interpret UV spectra. So it is known that in a gas phase, trisulfur radical has C2V belongs to C2V point group, and this is also the case for S3- radicals optimized in ultramarine lattices. For each type of considered stoichiometry, I found upon the optimization 2 different types of 2 different local minima with somewhat different S3- sighting and coordination to sodium cations. Trisulfur radical interacts with sodium cations mainly by the terminal sulfur bonds. Well, calculated geometric parameters are in decent agreement with the only available X-ray absorption spectroscopy data I am aware about, and the distance between S3- radical occupying the neighboring cages is always greater than 6 angstrom. The source of blue coloration in S3- radical is electronic excitation between the highest doubly occupied molecular orbital and singly occupied molecular orbital. which belongs to 2A2 and 4B1 representation in situ group respectively. The character of frontier orbitals for embedded trisulfur radicals. Okay, I forgot to tell some details about these smaller cluster models with water molecule only, but if you want, I can explain it later if someone wants to ask. But anyway, these frontier orbitals preserve their molecular character for embedded trisulfur species in cluster and periodic models. These frontier orbitals are rather well separated both in energy and spatially from the lattice states. So the negative charge is localized mainly at terminal sulfur atoms, whereas spin is more roughly more equally distributed over the whole radical with slight excess on the central atom. So in the UV spectra of ultramarines, one can see usually a very broad band centered around 600 nanometers. The calculated TDDFT values are in good agreement with experimental data. There are some small differences in the nature of this transition with respect to gas phase, because due to the lowering symmetry, there is more effective mixing between states. The most intensive electronic excitation is no longer pure 2A2 4B1, but has some admixture from lower lying 11A1 orbital. Also, this 11A1 to SOMO excitation appears as a satellite band. It gained in intensity in comparison to gas phase data and is shifted toward higher energies. The only exception is I found was the model in which trisulfur radical has the strongest distortion from to power symmetry, and in this the most asymmetrical species. The donation to SOMO occur mainly this 2A2 orbital has like the admixture of bonding 3B1 orbital, and the transition was the strongest transition was shifted was blue shifted. Actually, at least in some papers, such satellite band was reported in ultramarines. So it can be tentatively assigned to this strongly distorted trisulfur species. One of the main important methods to study radical system is electron paramagnetic resonance. So it was the next step in my studies. Calculated component of G-tensor are in good agreement with experimental data. What was interesting is that in experimental data, usually two types of paramagnetic centers was reported in ultramarines. One with lowering of temperature could be resolved into G-tensor component, and the other side give isotropic signal in wide range of temperatures. So the presence of these two paramagnetic sites was explained either as a result of different dynamical effect in sodalite cages, also as a result of the presence or lack of exchange coupling between the neighboring radicals. So I try to verify these both hypotheses. First, I calculated models containing two radicals per cell or per supercell. I calculated like ferromagnetic state with both spin aligned and antiferromagnetic state with opposite spin. in both cases, the energy was the same. So this indicates that there is no effective exchange coupling between the neighboring sites. The next step was to check the dynamics of trisulfur radical. So, well, to do it correctly, probably I need to do like ab initio molecular dynamics. I did it in lazy way. I just estimated this the rotation barrier of this of trisulfur radical along this along the y-axis in order to interchange this to average gx and gz component of the tensor, which deviate the most from the isotropic value. So depending on the model and on the coordination of S3- radical to sodium cations, this roughly estimated rotation barrier can be either pretty small or quite substantial. So on the basis of these studies, we can assign the difference in the observed anisotropy of EPR signal to different dynamical effect. There is also here are also models of containing disulfur radical, which seems to rotate freely. I will tell about this radical in a moment. Then I calculated these are gamma phonons to interpret available resonance Raman data. So we have like in S3- radical we have three possible modes: bending, symmetric, and antisymmetric stretching. Calculated DFT values agree well with experimental data. Again, this is probably some error cancellation between gradient functional inharmonic approximation, but it works pretty well. In the lattice, I can usually identify more than three modes containing these trisulfur motions due to coupling to the lattice states, and in the region of flow frequencies like below 100 inverse centimeters, there are also some modes due to partial translation or rotation of S3- radical within cage. So in summary, generally the properties of gas phase and embedded trisulfur radicals are quite similar due to the fact that frontier orbitals largely preserve the thermomolecular character. There are several possible orientations of S3- radical in sodalite cages of similar energy. There are some changes in electronic excitations due to lowering the symmetry in embedded species in respect to gas phase C2V symmetry. Okay, I didn't mention. Maybe I should mention. I have obtained the reasonable values of electronic excitations only if I applied long range corrected hybrid functionals. If I use in this cluster model gradient or hybrids, they were plugged with plenty of artificial charge transfer between trisulfur radical and lattice oxygen atoms. There is also no exchange coupling between radicals occupying neighboring cages, and the presence of paramagnetic sites with anisotropic or isotropic signals should be attributed to dynamical effect. So it was the first part, maybe hopefully the most boring one, and now it will be slightly more interesting. Before I proceed to red ultramarines, I would like to tell a few words about yellow S2- radical. So this is radical which frequently accompanies blue S3- radical in ultramarine. At high concentration, it can give like green shade of these ultramarines. So it absorbs light around 400 nanometers, and this is excitation between bonding p orbitals to antibonding pi orbitals, which are degenerated and contains one hole. Recently, this S2- radical was quite intensively studied due to its interesting optical properties like strong orange emission and photochromies. Regarding EPR spectra, these sulfur defects were studied for long in alkali halides. And unlike S3- radical, which usually gives quite narrow range of signals, they seem to be quite fragile to the environment, and the measured values of G-tensor cover a quite wide range. There is also there are also some controversy with the assignment of the EPR signal of this sulfur radical in ultramarines. So in early studies, isotropic signal with G value of with large value of 2.4 was assigned to the sulfur radical, but it was later explained as a result being due to iron impurities. Another assignment was a signal with quite low value of close to 3 electron value of 2.0. In 2011, these French authors claimed that they finally measured and undoubtedly assigned strongly anisotropic signal with isotropic value about 2.2, and the actual value much larger than the perpendicular ones to S2- radical. So in this study on S3- radicals, I included some preliminary data on S2- radical. Some of them were wrong. I found some errors in calculations, and now the process of refinement is ongoing. So for two types of stoichiometry, I found for each periodic models of this stoichiometry, I found single local minimum of energy. Then I cut cluster models as previously and use them for the calculations of spectroscopic data. Campbell-Philippe seems to reproduce the absorption energy quite well. The more challenging issue is to predict the value of G-tensor at DFT level, because it is governed by the splitting of this degenerated unfilled shell, this antibonding pi orbitals, and the splitting of these orbitals strongly depends on the model, on functional, and however, it seems that okay, so it seems that the G-tensor, so the computed G-tensor values are quite okay. So this is very anisotropic signal. Isotropic value is clearly much larger than larger than the value for S3 minus radical. So on the basis of this, we can reject some previous assignment of this signal. There are also notable differences between two models. So it seems that this suggests that even in ultramarines, one can see like more than one EPR signal from these sulfur radicals, depending on the environment. Again, there is no exchange coupling between the nearest radicals, and as I showed earlier, the signal can be averaged due to nearly free rotation of this radical, which also can make difficult to measure the components of G tensor. And some further studies in collaboration with Mariusz Radoń from Jagiellonian University, using also complete active space SCF approaches are conducted. Okay, so in the last part, I would like to talk about this so-called red ultramarines. They are called red, but they usually have some shade of violet or pink, because they contain both blue S3 minus chromophore, and in addition they have some red chromophore absorbing a green light around 500 nanometers. The identity of this red chromophore was for long was not explained. It can be assigned in literature either to the neutral tetrasulfur, to the tetrasulfur anionic radical, or even to S3 minus Cl molecule, because these red ultramarines were usually obtained by treatment of blue ultramarines with chlorine. However, in recent years, some red ultramarines or their analogs were obtained in chlorine-free processes. So it suggests that this chromophore is some purely sulfur-based species. It is, and these sulfur-based red pigments are quite interesting because they can offer a cheap and non-toxic alternative to some traditional inorganic pigments, which usually relies on heavy metal compounds. From both experimental and computational studies on sulfur vapors, it is known that the isomer of C2V symmetry of the neutral tetrasulfur absorbs green light. However, in the literature, there is still quite common assignment of this red chromophore to the radical species. So the purpose of my study was to check what is really this red chromophore in ultramarines. So again, I started from the optimization of periodic models. I considered models of various stoichiometry. So I have always one tetrasulfur neutral molecule or tetrasulfur anionic radical per unit cell. To keep all the system neutral, I put either a single sulfide or chlorine anion, or I remove one sodium cation. Then I cut cluster models consisting of the whole sodalite cages, and for them I perform this hybrid functional studies as previously. Additionally, for the gas phase tetrasulfur species, I performed some calculations using single point energy calculations using either coupled cluster NIFOs or complete active space SCF with second order perturbation corrections for dynamic the correlations with active space containing all 3p electrons. Okay, so these are all tetrasulfur isomers I considered at certain step of my work. These are not all possible tetrasulfur isomers, but some of them I excluded a priori, like I didn't consider linear isomer, which wouldn't fit into the cage anyway. I didn't consider some high symmetric species like tetrahedron or square because they should be unstable due to Jahn-Teller effects. In agreement with some previous studies on computational studies on gas phase species, the most stable isomer, both in a gas phase and embedded in ultramarine lattices, was always this boat-shaped planar isomer belonging to C2V point group. The next one was always for gas phase species. The next one was this planar C2H isomer. In the case of neutral molecule, it was about, in a gas phase, it was about 30 kilojoule per mole less stable. In the case of anionic radical, it was almost equally stable as C2V isomers. There were a few kilojoule per mole of differences, so it's like within the error of DFT. However, upon inserting this C2H radical into sodalite cage and optimization of periodic model, it converged to this twisted gauche C2 structure, which in turn was always unstable in a gas phase. If I try to optimize this model in a gas phase, depending on the initial torsion, it always converges to one of these two planar structures. The remaining, okay, so rectangular T2H isomer is found to be in a gas phase to be transition state between two C2V isomers. All these other cyclic or branch models are much less stable, at least 60 kilojoule per mole less stable, both in a gas phase and in the lattice. However, they are somewhat these more compact branched isomers are somewhat stabilized by putting them into sodalite cage, so the exact order of this energetic differences are somewhat different in gas phase and in embedded phase. Okay, so I will focus on this most stable C2V planar isomer. So for the neutral tetrasulfur species, the final geometry was always, regardless of the initial position, was always within the diagonal plane of the cubic cell, and it bonds to sodium cations only with these terminal sulfur atoms, which have slight excess of the negative charge. In the case of S4- radical, I typically found several types of local minima of energy with somewhat different orientation within the sodalite cage, and they could interact with sodium cations by all sulfur atoms. Okay, so the source of the most intense electronic transition in tetrasulfur species was always due to the transition between frontier orbitals, so between HOMO and LUMO in the neutral or the highest doubly occupied orbitals and SOMO in radical. Okay, so these are calculated UFOV spectra in vertical approximations for the neutral tetrasulfur species. So there is quite a good agreement between the CASICF data and DD-DFT data for gas phase molecule, and there are also quite similar for the embedded species. The only isomer of the neutral S4 molecule which absorbs strongly green light is this the most stable C2V planar isomer. In the case of the radical of the annealing species, that there are more discrepancy between both between KCCF and time-dependent DFT for a gas phase, which can be due to some problems that DFT has with the description of negatively charged species, and between gas phase DFT and embedded DFT. So generally, the most stable C2V isomer absorbs in the region of the near infrared. So it is beyond the scale of these features for gas phase. It is somewhat shifted toward the red region upon embedding. And the only S4- species absorbing green light are these high energy branched isomers. Okay, so this is G-tensor calculated for S4- radical. Okay, so isotropic value is very similar to slightly larger, but quite similar to the value reported for S4- radical, which means that from low quality EPR spectra, it can be quite hard to distinguish between this S4- and S4- radical. However, if the components of G-tensor are very different, so if one could obtain in low temperature EPR spectra results into components, this is the possible way to differentiate between S4- and S4- radical. And there are also calculated gamma phonons to interpret available Raman data. So from the resonance Raman, it is known that this red chromophore has these four modes: 670, 650, 400, and 150 inverse centimeters. And the best agreement between DFT phonons and available Raman data was found from this C2V isomer of the neutral S4 molecule. So these bands can be ascribed to starting from the highest frequency to symmetric and antisymmetric stretching of terminal bonds, in plane bending, and the stretching of middle bond. Interestingly, in gas phase, these two modes show accidental degeneracy. However, it is lifted when this tetrasulfur species interacts via these terminal bonds with sodium cations. And the agreement for the remaining isomers and S4- radical was much worse. So in conclusion, the only plausible candidate for this red chromophore in ultramarines is the neutral C2V isomer of the neutral S4 molecule. It is the most stable species. It strongly absorbs the green light, and its vibrational modes match Raman experiment the best. The presence of S4- radical, if it is present at all in ultramarines, can be potentially detected by the absorption of near infrared radiation, and possibly by good quality EPR spectra with resolved into components. And the last conclusion is maybe trivial, but not for everyone. The confinement of polysulfur species can affect their properties, like vibrational modes and electronic transitions. This is quite important because with this increasing interest in metal sulfur batteries, there is a lot of experimental data supported with some DFT calculations on the isolated gas phase polysulfur species, and they do not necessarily may describe the condensed phase as well. And okay, so I would. Okay, this is just the last slide. I would like to thank Piotr Pietrzyk from Jagiellonian University for his discussion on EPR experiments. Mariusz Radań from Jagiellonian University for the discussion on KCCF method, and to and to Pellegrit infrastructure for computational resources, specifically to the academic computational center Cyfronet in Krakow, and thank you for your attention.
Questions in the audience? Yes, please.
I'm curious about knowing something that maybe I didn't interpret correctly, but I understand that your periodic calculations always correspond to a neutral system, right? And then you jump to a cluster calculation. So the question would be very simple: how do you decide about the charge of the cluster?
Yes, the class. Very good question. Okay, so clusters were.
Because I see there, for example, 4, 6 minus.
Cluster were not charge neutral.
Yes.
Maybe it will be better in this. Okay, but I got in this case, I performed some test calculation on this large cluster for this trisulfur species, which were negatively charged, and then I also checked this smaller cluster with for convenience, for computational convenience, where I removed silicon and aluminum atoms and just left water molecules resembling oxygen lattices, and this cluster were positively charged. And for this both types of charged cluster, I got essentially the same result. So it seems that the charging of the cluster does not affect the properties I studied.
Yes, I have several, but one is a little bit related to this. No? You are putting, it seems to me that the problem is that you have sulfur inside the cage, and you don't know what the structure of sulfur is. Why so? Is not any method to really say the sulfur is in these positions? Any?
Okay, I think for
X-ray or
I think for X-ray crystallography, they are there is too much disorder to get this structure properly. I'm not aware of any. They can be oriented in various ways. You can only like about half of these cages occupied by in blue ultramarines, like only about half of the cages being occupied by trisulfur radicals, and so I don't think it is possible from X-ray crystallography to get this structure resolved, and maybe from X-ray absorption spectroscopy it could be better, but in theory, but probably you also have some problems with the interpretation of this XAV spectra, because you have like probably you have several closely situated edges from some different polysulfur species. And probably you also got some, like mainly mean values.
Mm-hmm.
So I think it's the main information about this are indirect from resonance Raman and paramagnetic resonance for radicals.
More. I have another question. It's concerning when you go to this EPR, you look at a little bit of the the spin signal and so on. You have said that you have put like two to see whether they are interacting or not. It seems that you, if I get it right for what you were telling us, seems that there is no any connection and between them from the electronic point of view. But
Yes,
can this material be doped somehow, or let's say increase this interaction more, in the sense that can you have like a electronically?
I haven't calculated. I wonder, for example, what would happen if, for example, one of aluminum would be replaced by iron 3 plus. Then maybe there will be some way for spins to interact. But in this, unless you have any paramagnetic impurity between these, I think these two radicals occupying neighboring cages don't see each other.
Mm-hmm. Okay. Nice. Oh, no. Then, if not, let's run the speaker again. No. The question about this is when you have it, you have a cluster, and you say 3 is when you go to 4, but in the 4 you also put the charge, but the clusters, the geometrical depends on the charge.
Okay.
No, the ground is.
But I take geometry only from periodic models, and in periodic models, I always have the neutral cell.
Yes, but what I'm trying to say, when you have, like, you go to the S4 radical, S4 minus radical, you say you are comparing S4 minus and S4 neutral. And then,
Yes.
But the structures could be different, whether it's neutral or is even as a free cluster.
Yeah,
Here you say these are these clusters, but.
Yes, I didn't optimize the cluster geometry. But I took structure from periodic models and from statistical calculations.
And then you prepare static calculations for the free cluster.
Yes.
And sometimes they are stable and sometimes it doesn't.
Excuse me? Okay.
That's normal
No,
because you have interactions around, no?
Yeah, but no. Maybe I should. Okay, I put some type. I didn't want to put something. I compare stability of S4 among them and S4 minus among them.
Yes.
So I always compare delta E between systems of the same stoichiometry.
Yes, but for instance, here you have S4 minus and you have S4 neutral.
Yes, but I didn't compare. Yes, well, they have different structures. Yes, of course.
Different structure, and even the order of the. You have different structures, but also the different structures, the energetic can change between them because one is charges and the other is not.
Yeah, but I didn't compare energy of S4 with S4 minus. I compare S4
one relatively to be one and the other.
The energy of S4 isomers with the energy of S4 minus isomers.
Okay.
Maybe it could be interesting to somehow calculate energy or free energy of formation in this system.
Yes, this kind of thing, the free energy, because the free energy.
I think it is.
It is done in this kind of defect things is done. We know how to do it. We are doing that. More or less. And this other image, this image that you put it there, you said that DFT didn't work. Also,
you mean as to mine? Well,
I was shocked to see such a big difference between one and the other. So then,
no, because I will
expect it that I will say as a free cluster, it will be different.
No, but I mean,
but when you have in a bulk, DFT will work also.
I mean, for ST minus, there is problem. I got some wrong results because in one case for this S2 minus models, in cluster calculations, I converged to the excited state wave function instead to ground states. As I check later. Yeah, but this is also the case which does not happen normally, I would say. But
only when you hold let's say, as a free cluster.
Yeah, but
they are different.
yeah, I mean,
But when you go to a bulk, I would say DFT will give reasonable results.
my worry for DFT was that the splitting, the lifting of degeneracy for this orbital, the size of splitting is crucial for the reliable properties. And my first impression was that maybe DFT cannot handle it. Now I am more positive toward DFT in this case.
Okay. Yes.
Yeah,
You have done very pretty accurate models, but I wonder if they were really a lot of accuracy. Okay.
Because in this one cluster model for this S2 minus radical, where the system converts to the excited wave function, because well, it's switched between this px and py as a thing of orbital. I didn't know about it. I calculated G tensor for this, and I got some physical values. So I was, but yeah, if everything is correctly done, I think DFT should work.
Nice work. A lot of you have read a lot about the business. Okay.
Well, I discovered it by accident. I repeated this calculation with newer version of Orca. They have somewhat different default SEF algorithm, and it converts correctly to the ground state.
On Monday we can discuss. I have some questions.
So querías preguntarle.
No, it was in relation to the conversion where you have made I guess that is absorption, but I don't know versus the wavelengths that you have these narrows at 500 nanometers, but yeah, here what you're representing.
He's saying that it has the gas and then the cluster.
Yes.
I say, well, the cluster should be between DFT and the other way should be pretty okay. But then,
well, here the argument is pretty good. Yeah, because it's,
but in the other one
yeah,
also
yes,
this is also should be very good. Why is not?
Excuse me?
Why is not?
Well, first of all,
this is a mess.
Yeah, but we have the charged species in a gas phase. So one thing is that
yeah, but in the gas phase, I agree that they should be different.
Yeah.
But in the cluster, they should be equal, and they are not.
Well, it's okay. They are different, but it's okay. So there are two models of different stoichiometry, and there is, in each case, there is a slightly different interaction between this charge radical and sodium cation. So it can induce some shifts, I guess. But yeah, well, it's like the general conclusion was that but this S4 minus radical is not the most stable isomer does not absorb green light, so it's not red chromophore.
I think Andreas, that is something that Joseph is doing. I think that here clusters and is key for giving the right color.
Huh?
You cannot get the red one. The red one is experimental one with clusters.
With clusters.
No, with sorry. But the cluster probably yes. Is what I think. That is related to the size of the particles.
Size of the particles.
Yeah, well,
is what is the same as what
it is not the red is
the experimental one says a mix between the size of
molecules
and the intrinsic.
Yeah, and the second thing is that this the actual color of
the questions I have, which is the typical size of these particles, interparticle, because typically it's the one that is the most important parameter.
Well, it is
governs the color.
Yeah,
for the color, you say.
Yes.
It is powder, so I guess.
It's powder. It's not something that I wanted to ask you. If it is a powder state, probably the color is very much influenced by the size
Yeah.
of the
What we are
particle.
doing, we calculated the properties with these
Linear
models, and
and it's very
then we
important.
plug it to see the particle size.
Yes.
But also this model is
But also I have related, well, maybe on
Yeah,
Monday or
although-
Tuesday we can discuss something because now we are doing, funny, some kind of concretes with zeolites. Okay. But
you're doing
they are
concrete
white,
with zeolite.
but they are only white.
only.
And this can be very interesting because it was on
Color.
the, maybe we can play with your this marine blue or red or yellow marine to make it's possible to get this kind of in the market to buy this
Yeah,
kind
these
of
are
zeolites.
Yes.
these are
Because then we can do
commercial sample. Yeah.
it's commercial samples. I will explore.
Because-
Maybe we can do with
Anyhow, you are working with
color.
experimentalists, no? These guys.
Yeah, I have one. We have one combined experimental computational paper in preparation, and the experiment is done on commercial samples.
Commercial samples, or you can prepare it, and because these are the point is that there are interest in this semester in this.
To see if we can do it.
I think once I saw some experimental paper when they report this S3 minus radical in some cements or something.
Yes,
Is what I want, but there are pure, I mean, the big amounts. To use zeolites like the raw material for making cements, and something that we are doing now. But typically they are white, and it's just to have a palette
but
of colors, you know, not only white. We can decide which color.
Probably you could have like blue cements with zeolites.
It's what it can be very interesting.
There are analogs of this of ultramarines done with cements. This I think this Kowalak did it. Yeah, concrenite, erionite for sure. Probably also.
Which one?
The concrenite and erionite for sure.
Yeah. This kind of materials are employed. It's typical employed.
Mhm.
Yeah.
Okay.
Good.
So
See you
you-
next week.
You're going for lunch? You want to come?